Extrema on an interval. This is section 3.1. This is one of the easier topics. However, it's so easy, people forget this topic. This is the extreme value theorem. We even had a quiz on it. We will have a quiz on it, whatever. So one of the things we're going to be investigating in chapter 3 are these questions. Does f have a maximum value on an interval? Or capital I stands for an interval, whether it's open or closed, it doesn't matter at this point. Does it have a minimum on that interval? When is the function increasing? When is the function decreasing? All right. Now, function does not have to have a maximum or minimum on an interval. Okay, so here we have an example. In this example, let's zoom in a little bit. Take a moment to zoom in. All right. So we have this is a closed interval, right? What I mean by closed is that it actually ends here and ends here, right? There's nothing weird going on. So there is a maximum value up here and a minimum value down here. So this one does have a maximum and minimum. But look at the second example. This is an open interval. What makes it open? I want you to notice that the open circles at the endpoints. So it's open over here. So if it's open and that's the highest point, it looks like the highest point, but it's not considered having a maximum. Why is that? Well, you can't actually reach the value of 5. Right? You can get close to it. You're approaching it. So there's some confusion here because in calculus, we talk about limits. Where is it going? But when we talk about a maximum, we have to actually reach the maximum. We can't say it's approaching 5, right? Because this is not a limit. What is the actual value, right? We get 4.9. Well, you can get closer to that. You get 4.99. And again, you can get closer again, 4.999. So you cannot get there. So there is no maximum. That's the so we say there is no maximum here, but there is still a minimum. Okay. And this one, there is an open hole here, right? So this is not continuous. So there's no minimum, but there is a maximum. All right. Now the extreme value theorem, I got to zoom out on this a little bit. Zoom out. All right. The extreme value theorem assumes two things, or has two conditions. One is that the function is continuous and that it's a closed interval. So two things. It must be continuous, the function must be continuous, and the interval we're looking at must be closed. Then you are guaranteed to have both a maximum and a minimum on that interval. Now, it's not saying they have to be different. So if it's a constant, right, if I have a function that's a constant, say 2, right, on the interval from 1 to 3, then from 1 to 3, the maximum and the minimum is 2, okay? Let's look at the example they give us. We have a function, and they're saying that there is a maximum here and a minimum here. And if this is a closed interval, let's say it's a closed interval, that's our guaranteed max, and our guaranteed minimum is over here. Okay, so this is actually kind of a weird example. So let's skip that for now. All right. So we're looking at definition of relative extrema. So relative extrema is an extrema that's just higher than anything around it. So let's look at a relative max in this example. This point up here is considered a relative max and an absolute maximum, right? It's higher than any points around it, so that's relative, but it's also higher than all the points of that function, so it's an absolute. Here's a relative maximum because it's higher than any of the points around it, but it's not the absolute maximum because it's lower than the maximum over here. We have a relative minimum here because it's lower than any of the points around it, but it's not the absolute minimum because there's one lower than that. Over here, we have a relative minimum because it's lower than any points around it, but this one is also considered an absolute minimum because it is lower than any other point on this graph. Okay? All right. Now, let's say, let Queen label all relatives and blah, 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 blah. Then label the value of the derivative of each of the relative extrema. Now, So the endpoints, endpoints are special in the sense that the derivative doesn't matter what happens at the derivative. But the ones in between, something special happens with the slope. The slope is going to be here. It's horizontal line. So the slope is 0. So the derivative is 0 at these relative extrema. Let's go on to example B here. So right now this is an open interval. Notice there's arrows, so I'm continuing from there. It's unbounded there. All right. So we'll look at what's going on here. That's 1, 2, 3, 4, 5. So at -5, we have a relative maximum, and the derivative is undefined. Whenever you see a corner like that, the derivative is undefined. Here at -3, we have a horizontal tangent. We have a slope of 0. At x equals 0, we have a horizontal tangent. At x equals 2, we have a horizontal tangent. At x equals 4, we have a horizontal tangent. Now, x equals -5, -3, 0, 2, and 4 are called critical numbers. So whenever the derivative is equal to 0 or undefined, these are critical numbers. Continuing. So, definition of a critical number. Let f be defined as c. So c must be in the domain of the function. If the derivative is equal to 0 or f is not differentiable as c, then c is a critical number. Now, that does not mean there is an extrema there. Okay? It's just a critical number. All right? Now, if f has a relative minimum or maximum at x equals c, then c is a critical number of f, and that doesn't count endpoints. Okay? So generally, I guess we don't talk about endpoints as being relative max or min. All right. Guidelines for finding absolute extrema on a closed interval. First, we find the critical numbers. That means find the derivative, set them equal to 0, and find out where it's undefined. Evaluate those critical numbers into the function, and evaluate the endpoints. So this is actually using the extreme value theorem. And we'll just make a chart. So that's the theorem. I'm going to stop the video here and do the examples in the next video.